Hey, so let me share my screen.
And also, would you like to share your slides as well?
Yeah. Okay, so can everyone see my screen?
Yes.
Okay, so hi everyone. Today
I
we're
mean,
going to
would you
be
like to
talking about.
share the URL of the slides as
Oh,
well?
sure. Okay, so yeah, hi everyone. So today we'll be talking about reinforcement learning 102, which is from values to actions, how reinforcement learning actually works. Before we start, I want to share something very exciting. I'm currently hoping to restart on two of the reinforcement learning projects that I started last year, and they are open for collaboration, which I'm hoping to start in June. The first project is a Q-learning survey, and the goal here is to understand Q-learning and its deep variants. And the goal of this paper is as follows. The first one is to have a unified taxonomy of the Q-learning and deep Q-learning algorithms. The second aspect is to have empirical comparisons, basically means that we collect benchmark results from the original papers. And thirdly, we wish to analyze real code bases and all sorts of aspects you can think about. And my second project is a IL survey, which is called Project Q because I think it's a cool name. Here, the idea is to organize IL methods beyond standard category. So remember that in this lecture series, we classify them into like value-based, policy-based, and actor-critic. However, we may wish to classify them into some other categories, such as discrete versus continuous action spaces or even some other ways. And we also wish to do more practical benchmarking because typical RL survey papers they do not do any sort of experiments. So if you are interested in research, this is a great chance to get involved early. And you do not need any prior research experience, and you just need curiosity to participate in these two projects. And I will be iron out more details in the next few weeks. Any questions?
Oh, can you summarize value-based versus policy-based learning?
Yes, policy value-based basically means that I have a network to estimate the values of state action pairs. Policy-based means I just have a policy network, like it basically tells me what action to take next instead of just computing the values. And then hybrid means we combine both.
Mhm.
So, so any other questions on these two projects? Okay, if no question, then
One
sorry.
question,
Yes.
in order to collaborate, like, how do we collaborate? Like, is it like we meet every week or
Yeah, we're probably going to be meeting every week after the project starts. Yeah,
okay? And how can I show my interest? Like, where should I reach out?
you can DM me and then I will be, yeah, feel free to DM me and then I will collect all the names and then in June we can decide how do we want to start projects.
Where
Okay,
to DM you, man?
Discord, yes.
Discord.
Yes.
And maybe, okay, I can help with sharing your Discord if you
Yeah,
want.
yeah, yeah, sure, sure, sure.
Okay.
thank you.
Thank you.
Okay. So, all right. Uh, so I just shared this.
Mm.
Mm, okay. So this is his
Mm.
Toby's Discord name.
Yeah, and then feel free to read the draft of these two projects. Yeah, the first one is more, I think it's more grounded, and then the second one is more incomplete. Okay, so back to today. So there are two ways to learn reinforcement learning. The first camp is what we call value-based methods. And the key idea is we learn how good actions are, and then we choose the best one. Or we can skip that step and directly what actions to take. And this lecture we will split into two halves. The first half we will study how we evaluate actions. Basically, value will lead to action. The second half will be about how can we act directly, basically direct action.
Also, just want to quickly mention before you move on,
Yes,
it's that so all of this will be finished in the next half an hour each, and then less than half an hour, and then we will be talking through code demo from Elp, and then we will open the floor for Q&As. So and also for anyone else that happen to have some relevant topic that want to present around today's topic, feel free to prepare them, and then we'll try to give everybody a little bit of time during those sections as well. Okay.
Yes. And if you have questions, feel free to interrupt me.
Mm-hmm.
So, last lecture we discussed what is reinforcement learning, and this lecture we want to discuss how do agents actually learn. So, for example, imagine that you are training your house cleaning robot. How does your robot learn what actions are good? Last week we defined agent, the environment, the reward, and basically, how can we turn interaction into learning? And experience alone is not enough. We need algorithms. So getting back to what we just discussed in the last slides, imagine training your robot to clean your house. You may teach it in two ways. The first way is to teach it to evaluate actions. For example, if the robot is in a dirty square and then there are probably a few actions, you can teach your robot how to evaluate each action. For example, clean the area or move to the next square. This second camp, you can teach your robot to learn to act directly and basically ask, what should I do right now? And these two approaches lead to very different algorithms. For beginners, it's very simple. You either evaluate first, then act, or you act directly. For engineers, these actually are two algorithms typically. The first value base, we typically have Q-learning or deep Q-learning, which we'll cover in the next few slides. The second category usually leads to what we call policy gradient. And finally, for researchers, we define them as two frameworks, and we call them value-based methods and also policy-based methods. And each method has a lot of methods in each of the category. And so, what is the intuition behind value-based methods? And the key idea is that we typically want to learn a Q function. Basically, we try to estimate how good is a state-action pair. And the core method here is that if the agent knows how good each action is, it may simply choose the best action. And your robot may just need to know what action is best right now. And that's it. So the problem becomes how can we estimate how good an action is? And basically, this will directly lead into Q-learning. For beginners, you simply need to know that this is learning how good each action is, and then pick the best action. For implementation purposes, we try to learn a value function, basically can be a table or just a neural network. And finally, for researchers, we may want to ask the question, can we ensure the learn function converge to the optimal Q function? That is, can we accurately estimate basically the what do we call the cumulative discounted reward that we discussed last week? And so now it's natural to ask, how can we represent such a function? And to simplify things, we may use a Q table. And imagine we have a 2D table, and each entry of the table answers, if I take this action here, how good is it? So imagine your robot has a table in its head. For every situation, let's say every square in your room, and every possible action, let's say go up, go left, go right, and also to clean the area, and it stores how good such pair is. And this is what we usually call a Q table. And the question is, how can we update this table, which we'll discuss in the next slide. And this table basically tells us how good that action is. If I'm here, how good is this action? For beginners, it's basically learning from experience because when you train your robot, you let it explore your environment. And the goal is to update the table over time. And for implementation purposes, we just maintain a 2D NumPy array, and then we update using some mathematical rule. And for researchers, we'll know that this is an off policy algorithm because when we collect the data, we may use some random policy. However, the policy that we are trying to learn, or the Q table what we are trying to learn is actually a different policy. And so basically, we learn optimal behavior independent of your current exploration policy. So now let us look at the equation. How can we update the Q table? So do not be scared by this equation. It's actually not so bad. We basically compare two things. The first thing is the QSA. So QSA is what we are predicting as the Q value. Now the second part of the equation, if you look at R plus gamma, so R is your current reward, basically what actually happened. The max A prime, basically, we are trying to estimate how good is the state S prime is by looking at what action is the best in the state S prime. And basically, this is how we move our estimate toward the truth, hopefully. So gamma is basically discount because the future reward has to be discounted. And alpha basically means how much do we want to update your Q table, because this R plus gamma minus Q is sort of the difference between the prediction and sort of the ground truth we can think about. And so it's like we just want to compare what we expected versus what we got, and we just learn from surprises. And for implementation purposes, we update with using three things. The first one is the immediate reward. The second thing is the best future value, basically in the next state as prime, and we want to look at what is the best action there. And we combine these two values to form an estimate of the QSA. And we call this the TD error, which is target minus prediction. And for research purposes, we call this temporal difference learning. And this is a bootstrapping method because we are trying to update QSA over time. And this converges under certain conditions, which you may read the original Q-learning paper. They have some proof there. I'm not going to worry about the proof here. So let's give a brief example of how Q-learning may work.
I say, Marius, have a quick question. Maybe.
Oh, sure.
Yeah.
We
I
also,
want
by
to
the
ask.
way, just want to say to everyone is that we take occasional questions within the first like 20-30 minutes of the presentation, but we'll accumulate most of the question to the end. Yes, but now I think we have time. So Marius,
Yeah, sure. Yeah.
Yeah. So the model always receives an reward, always, in any case. And
What does he receive?
reward. You
Yes,
said that
yeah.
R is the reward, and
R is rule, yes. So basically, you train your robot in the environment, and then the environment will give out some sort of reward.
And the more precise is the prediction, the higher is the reward.
The reward is tied to the goodness, sort of the goodness of the action. So imagine you're cleaning a robot. So if the robot clean the square, you probably want to give a reward of +1. And if the robot move to somewhere else, you may want to give a reward of 0 or -1. And typically humans have to decide what kind of reward to give.
So it's a variable too.
Yeah, it's kind of variable, but usually it's human designed.
Oh, okay. Thanks.
Okay, so now let's look at a simple example of Q-learning. So imagine we have a 3x3 grid, and we wish to let our robot to navigate from the first square to this square. And S is the start, and let's assume we have a goal reward of +10, and let's say we have a reward of -1 for every other square. And let's say X is an obstacle. So basically, the goal is to have the robot explore the environment. So let's suppose that it generates a trajectory of 1, 1, and then 1, 2, and then 1, 3, and then 2, 3, and then it reaches goal at 1, 1, 3, basically. And so let's say we are trying to learn from this trajectory, and we can record the reward here. Basically, for each step that is not reaching the goal, we give a reward of -1. And when we reach the goal, basically 2, 3, we give the reward of +10. So let's bring back the equation. So we start with the state 1, 1, basically the left corner. And the action is to take right. And let's say we get to the state of 1, 1, 2, basically the square here. And initially, we almost always set the q values to 0. So this term, the max a prime q12 a prime is going to be equal to 0, because in this state, all the action leads to a q value of 0. So this term will basically become 0. And the QSA term, the original, is also 0. And alpha, let's say we wish to use 0.5 for simplicity. We can also always use other values, for example, 0.9. And R, we receive a reward of -1. And gamma is basically how we discount future reward, and typically we use 0.9. And this value becomes 0, and the 0 is the original estimate. And we compute the value, and this will become -0.5. And so after a first iteration, we update the q value for this square, and it will become -0.1. And as we go along this trajectory, we will update different state action pairs. And the goal is we let the robot explore as much as possible, and then hopefully the Q table will converge at the end. So for beginners, so basically the robot tries to learn the step by step, and good actions near the goal will become valuable. Those Q values will become higher first, and early actions will also update as we go. And basically, we update uses the immediate reward and also the next state value. And this is what we call the bootstrapping, using the current estimate of the future to update the current state. And finally, we call this temporal difference learning, or TD learning. And you can also call it value propagation via environment updates, because sort of as we go along the trajectory, we are propagating values to the previous states. And hopefully it converged towards the Q star that we wanted to go. So now you may think that Q table seems fantastic, but it's not. And when does the Q table breaks? The issue is if there are too many states and actions. For example, if your room becomes too big, like if you are cleaning a palace, you may have millions of squares, and your robot is not going to store such a huge table, and we need something more scalable. And this is what we call a neural network. And here, basically, similar states will basically share some sort of abstract information through the network. So for beginners, basically, we replace the table using a neural network. Instead of just storing actual values, we predict them. Basically, your network, we're taking some state, we're taking some action, and you have some parameters, theta, and the output typically be Q values for actions. So for now, we assume the actions are discrete. For example, going up, going down, going right, going left, and also to clean the square. And the insight here is that this is what we call a functional approximation of the Q table. And the goal is we wish to achieve generalization across states, because since the states are continuous, we will not be able to encounter all the states. So you will hope that the neural network can generalize. So now let's look at a simple DQN architecture. So basically, in the left side, we feed in the state, and basically this is the input layer. And then afterwards, the output will be Q values for each of the states. And then we simply choose the best action, or choose some random action at 10% of the time. And basically, we take this action, and the environment will give us some feedback reward. And basically, it will give us the next state. And the idea is that, remember that previously we used this update rule to update the Q table. Now the goal is we treat this difference as some form of a loss function. And basically DQN tries to minimize this loss function and to approximate the Q function. So basically for beginners, this network predicts how good each action is. For implementation purposes, the input is typically a vector, and the output is also a vector, basically represent the Q values for actions. And for research purposes, this is learned via gradient descent. And typically, you just use the Python library to do it. So DQA is great, but how can we make it a bit more stable? If we just train it using the raw method, you'll find the training can sometimes diverge. Because the first reason is the data is highly correlated. So remember that in supervised learning, for example, if we want to train an image classifier, we may have millions of images, and the core assumption is that each image is sort of independent from other images. However, in IL, this is not true because if we are in a state and then we take some action and then it goes to the next state is going to be definitely correlated with your previous state, and so on and so forth. So how do we solve this problem? This is typically we use a replay buffer. Basically, we store most of our past experience, so it depends on the size of your replay buffer. We store them and then later we sample from them, and then so we hope that the data points are kind of independent. And the intuition here is that we don't learn only from the latest experience, we actually learn from many of the past experience, and this helps to keep the target stable. So for implementation purposes, we basically have a replay buffer. Basically, it's an array that stores the SAS prime pairs. And during training, we sample random batches of them, and this can help break correlation. And the second technique is what we call the target network, because if we look at this thing, so remember that we are trying to estimate the difference between these two terms. And when we are trying to estimate the target, we are sort of using our own network to compute the target. And basically, the target will sort of be moving because as we update our network, then the target will also be shifting. And this can be problematic. To solve this problem, we use a separate target network. Basically, this network is a copy of your main network, and then we periodically copy from the main network to the target network, and this will be used to compute the stable targets. And the goal of these two approaches to address the non-IID problem and also the moving target problem, and is shown to improve training stability and convergence. So now we are ready to put everything together. For beginners, it's just we try different actions, we collect experience, and we learn from the past experience, and we slowly improve the prediction. For implementations, we mention replay buffer, the target network, and also the mean square error loss. Basically, we measure the difference between prediction and target. And for research, we call this the off-policy learning and also bootstrapping with functional approximation. And it's trying to approximate the Bellman optimality equation. And so
I'm
we
sorry.
are ready. Yes,
May I ask a question?
yes,
About the loss function.
yes.
How the prediction looks like? Is it a number and the target is a number too?
Yes,
Then
it's a number. So QSA is a
yeah.
number, and the target is this term, R plus gamma max A prime QS prime A prime. This is also a number.
And if we will consider robot
Yeah.
vacuum cleaner, robot
Yes.
vacuum cleaner,
Yes.
how will be the prediction, the ground truth value will look like?
So
And
so we assume this is the ground truth. So R plus gamma max A prime. We assume this is the ground truth, basically.
Mm-hmm. And QSA is prediction.
Yeah, QSA is a prediction.
And the loss function is just a minus between them.
Yeah, minus between them, and then we average over many examples.
Okay, great. Thanks.
Nice. So now we are ready to look at the pseudocode of it. So remember, we first initialize a replay buffer. It's basically an array to some capacity, typically 1 million or 10,000. And we initialize a neural network, basically, typically with random weights. And basically, we will train our robot for M episodes, let's say 1,000 or 10,000 episodes. We first initialize a sequence, basically a sequence of axes. So axis is typically like state action and next state pairs. For each of the episode, we will typically set a length to be, let's say, 1,000 steps. For each step, we first select either basically with epsilon probability, like for example, point 1, we select a random action 80, or we select an action that seems to be the best, and we execute the action. Basically, we ask the robot to take the action in the environment and observe the reward RT and the next state xt+1. And we will basically set the next state to be this one. So st, at, and also xt+1. And we will basically store the transition, basically st, at, rt, st+1 in D. And during training, we basically sample a bunch of, let's say, 64 transitions from the buffer. And then we will compute the target. For terminal state, the target is just the immediate reward. For non-terminal state, basically, you will be the reward plus the term. So this is, remember, this is the prediction term. Basically, we estimate in the next state what is the best possible action. And then we perform the gradient descent using this loss function. And this is the basically the DQN pseudocode. And this can be implemented in CleanRL DQN, and all of you can demo in the next few in after this presentation. And the CleanRL has a very nice single file implementation and clear training loop. And basically, there are many different important functions. For example, env.step basically takes the action, and buffer is the replay buffer, and update is the gradient step. So now DQN methods seem to be great. So, but sometimes it may not work, and especially it struggles when the action space is large or even continuous. So for beginners, you just need to know that it's hard to handle continuous actions because we assume that the Q values has to be basically we output an array of the Q values. However, if they are continuous, it's hard to do that. And for practical implementation purposes, because we have to sort of compute a maximization function, and if the action is continuous, then it's not clear how can we do that. And for researchers, this represents many different challenges. For example, the most important one is the overestimation bias because your Q value is probably going to be higher than the actual cumulative reward. And also there are stability issues within Q-learning as well. So the key idea is that sometimes evaluating every action is actually harder than just learning what to do. And so now we can naturally discuss the policy-based algorithm. And this works well when the action is spaced and continuous, and also works when the action is discrete. So instead of evaluating every action, what if we just skip that step entirely? So let's bring our robot example back and let's assume it's discrete again. So if the tile is dirty, you should just clean it. If the tile is clean, just move to the next tile. And we do not need to compute Q values for every possible action. And so basically, yeah, you don't have to compute the value for every action. And for implementation purposes, it's also another neural network that basically learns a policy. So basically, give the state, it actually outputs a distribution of the actions. Basically, so let's say if there are 4 actions, I just output an array represent the probability. Or if the action is continuous, it could just be some sort of a Gaussian distribution that is represented by a mean and also a standard deviation. And this way, we can directly map states to the action or action distribution. For researchers, we basically optimize what we call the J theta. So last week we talked about the expected cumulative discounted reward, and for now we just call it to be J theta, and we just directly improve the policy. And so now let's look at another equation. So don't be scared again. So the idea is actually very simple. We wish to increase the probability of actions that lead to higher reward. So this lower triangle basically is the gradient step. So the loss function is actually this term, the gt times log pi as. So the idea is that we want to increase the probability of what we call the good actions. So GT is you can think about as the cumulative reward. So basically, so let's say I have a trajectory of 1,000 steps, and at each step I can estimate, basically I can compute the total reward from this step until the end. And for each step, I also have a distribution of the possible actions. And basically I can compute the probability of the actions that I picked. So using this loss function, we can increase probability of actions with high reward, and we can decrease probability of what we call bad actions. So we basically learn from the reward directly, and for implementation, we use the reward to update our policy network, and this will scale update by how good the outcome was. And for researchers, we give this a term to be unbiased gradient estimate. So basically, we use this limited information to estimate the gradient instead of taking the expectation, because this assumes we have infinite trajectory. So what does it look at in code? So this is slightly inaccurate. So the idea is that we take some action using our policy, using the current version of the policy. We store the log probability of the policy, and we compute the reward. And then after we complete a trajectory, we can compute the loss function using this formula, because we want to minimize this term by basically, so this is kind of taking a sum of all the product, and each product is multiplied using the cumulative reward from that step to the end, with times the log probability, and we update our policy using this loss function. As for beginners, basically we try an action. If the reward is high, we'll do it more. If the reward is low, and we do it less. And for implementation, we have a bunch of terms. The log probability, basically how likely the action was. The reward is still the learning signal, and loss is the loss function. And for researchers, we basically try to estimate the gradient using sample trajectory, and this will scale the update by the return, which we call the GT. So now we can finally compare the two camps of methods. And we have the value-based method on the left. Basically, we learn how good the actions are, and the output is typically a Q function. And we take the argmax over the Q, and the strength is typically will be stable and it will be quite efficient. However, it's very hard for continuous actions because of the argmax problem. And so for policy-based methods, we learn what to do directly, and the output is basically a policy, and we basically sample from the policy to select action, and the strength is flexible and especially good for continuous actions. However, one problem is that it actually has high variance because we sampled trajectories, and you may got very different reward values. So now we can go to the recommended reading. So if you are interested, you can read the original DQM paper from 2015, the Nature DQM paper. And spinning up in deep IL, this has very nice documentation from OpenAI, and it has clear, intuitive explanations. And if you are feeling very brave, feel free to read my Q survey projects and also IR survey projects, and we welcome all of you to contribute towards some form of a publication. So key takeaways for today's discussion. So there are two main ways to learn IL. The first one is value-based. Basically, we learn a value function, the Q function. And the second way is to learn a policy. Basically, we denote as the pi. And value-based, typically the DQM. For policy-based is typically the policy gradient method. And both aim to maximize long-term reward. So despite the different methods, they have the same goal underlying. So what's next? So can we combine both of these approaches? And this were what we call the actor-critic methods. So your actor is your policy, your critic is your value network. And these methods will basically learn value and policy together. And this will proven to be more stable and also more powerful. And typically, this is what we do in the modern IL applications. So any questions? This is the end of this.